This is the set of notes on heating curves. You can see there, I've got a couple examples of what a heating curve is. You might look at it and say, well, those aren't curves at all, that's just a bunch of lines. Well, the deal is in math and science, a lot of times we use the word curve just to mean graph, and so this is a graph that shows what happens to a substance as we add energy to it in terms of its temperature and its state of matter. And I'll get into breaking down some of the more specific parts of this as I go on. So the first question, what is a heating curve here? You can see it graphs temperature versus energy. So usually that comes in the form of like heat that we're adding to it with a Bunsen burner or with something else, and we then look at the temperature and how it changes. The other thing here is indicated on it, we have phases and we have the changes, which is like boiling and melting or freezing and condensing, depending on what curve we're looking at specifically here. And as I said, I'll get into talking about more specifics about what each of those parts is here in a second. The next thing to notice here is that each one of these, each substance has its own heating curve. So if we look at this heating curve, take a second, try and figure out what substance this heating curve might be for. If you want to pause the video and try and think about it for a second and then unpause it. Okay, so thinking about it and looking at the temperatures that we have associated here, what happens is the crucial numbers here, the melting point is at 0, the boiling point is at 100. So you might have identified that that goes right along with water. And that's actually what these heating curves are for. So each substance has its own unique melting point and boiling point. Also, a little bit more specifically, there's a ratio here between the amount of energy added to melt it versus the amount of energy added to vaporize it or boil it, and that's unique for each substance as well. So you can actually identify a substance just by looking at its heating curve. So we're going to keep on breaking down the parts here. Some of it's kind of repetitive, but just to make sure that you really understand all of the different things. So just teaching you how to read this, anytime that you see temperature changes occurring on this, it's in a sloped section. So here we have a temperature change for a solid, here we have a temperature change for a liquid, here a temperature change for a gas. If the temperature is changing, that means kinetic energy is being added, because temperature is literally the average kinetic energy. And so that means the particles are speeding up, they're moving faster during those sections. The steeper the slope we have here, that means the faster the temperature is changing. So if you remember from the last unit, if something changes really easily, like a metal, it has a low specific heat. So steeper means it changes temperature pretty easily, and that means that we'd have a low specific heat. So during this section, if you're trying to find how much energy you're adding while something is changing its temperature, you just use the Q equals mc delta T equation during those periods. So the other part of this curve is when the temperature is constant, where it's a flat horizontal line. And this is not representing a temperature change. It's not representing a change in kinetic energy, because if kinetic energy was changing, it would have a slope to it. It doesn't. It's flat. And so this means the potential energy is what's changing. As you add energy in, you're adding potential energy. And what that goes into is spreading the particles out. So two particles want to be together. You put energy in. You pull them apart. You're adding potential energy in there. The length of these periods of the graph represents the relative amount of heat of fusion or heat of vaporization that we have there. And so a long horizontal line means a lot of energy would have to be added, which means it'd have a high heat of fusion or high heat of vaporization. When you look at these charts, you might notice that the heat of vaporization is larger than the heat of fusion on the chart. That goes along with the concept of what we learned back in the last section. So the longer it is, higher heat of fusion or heat of vaporization. And if we're in one of these flat portions, we're talking about a phase change. So what we're going to be using is delta H equals mass times heat of fusion, or delta H equals mass times heat of vaporization. A phase change, there's no change in temperature. So summarizing that all up, we have this graph here. I'm going to talk about the different parts. So first, what we're going to do is we're going to label where kinetic energy would be changing and where potential energy would be changing. If you want to go ahead and try and do that yourself, you can maybe test your knowledge or understanding of that and pause the video and do that. Otherwise, I'm just going to go on and explain it. So these three sections, there's a slope. That means the temperature is changing. If the temperature is changing, the kinetic energy is changing. The other two sections here, this is where it's flat. That means potential energy is changing. We're pulling the particles further apart. We're getting an increase in potential energy. What's happening down here, we have a solid and the temperature is changing, so we're heating it up. Then in B, the next thing that happens, we get to this melting point here for water to 0 degrees Celsius, and then we have to melt it. So we have a phase change here where it's melting. The next thing, C, is a liquid. We're going to be heating it up. After that, we get to the boiling point, and so we're going to boil it. So D is boiling. Another phase change. E, all of it's been boiled as a gas, and we're heating it up. So understanding these specific sections of these heating curves is going to help you know how to do these problems quite a bit better. So what equations go along with each of these? Well, I said if it's a phase change, we're using mass times heat of fusion or mass times heat of vaporization. This one down here is melting or freezing, so that's associated with heat of fusion. The one up here, heat of vaporization, boiling or condensing. For the rest of these three, we're talking about a temperature change, so we're using Q equals mc delta T, although keep in mind that the C depends on the state of matter. For solid and liquid and gas, it's all different specific heats, even though they're all water, so that's really important.